All right, welcome back to another episode of Scientifically Simple. My name is Brandon. Today we are going to be discussing valves, some kind of fundamentals of valves, and then delving a little bit into relief valves, something that is pretty critical in engineering applications. Without further ado, I'll hand it over to Mo.
Okay, everybody, again, good morning, good afternoon, and good evening.
Hey, Mo.
For whoever gonna be seeing that slideshow that we are going to be presenting today. So, as we have mentioned in our last episode, how a project engineering execution looks like, and what's the role of a process engineer, we are going to be now taking it more granular, where we are going to be targeting every single process unit in a chemical plant. So a chemical plant has if we might call it that way, there is elements of a chemical plant, small pieces that you put them together that will be forming the overall chemical plant itself. So that those processes can be split into two main categories. There is the process units or standalone process units, and there is the piping system. The piping system that will be consistent of valves, pipes, fittings, steam ejectors, and even subcategories of valves, what we're going to be talking about later in this episode, which is the pressure relief valve. The second main category, which are process units, those are again, this is not an exhaustive list, this can be more than that, but it can be, you have your reactors, you have your separation units, you have a pressure change unit, and a temperature change unit. So a reactor, everybody's aware of it, it can be a batch, a mixed reactor, a plug flow reactor. It can be used for a biochemical reaction, it can be used for a refinery catalysis. For separation, that's pretty much any type of a physical processes that are separating two or more components based on a given physical property. So if we're talking about volatility, relative volatility, that will be distillation. If we're talking about relative solubility in a third fluid, then we're talking about solvent extraction. Pressure change, that's pretty much any unit that either depresses the pressure or build up pressure. If it's in a liquid, it's going to be a pump. If it's going to be in a compressor, if it's in a gas phase, it's going to be a compressor. If it's a turbine, which basically goes out the other way around, is basically reducing the pressure while doing work. Temperature change, that's pretty much any type of equipment that relies on heat transfer, conduction, convection, and radiation. Radiation, you're gonna see that mostly in furnaces. Conduction and convection, that's gonna be mostly in Schillen tube heat exchanger, which is the most standard type of way of doing a heat transfer. Or it can be in a more special type of heat exchangers, like a spiral heat exchanger or a plate heat exchanger. But again, the details of that we're gonna talk about later as we go on each one of these steps one by one.
I am very excited for
today, that. I know you have been too. Yeah, I know you have been really. Yeah. So our today's discussion is going to be around the valves. And valves are pretty critical because you are gonna have all different type of valves categories, whether it's just shut-off valves or valves that want to be regulating pressure or regulating flow or regulating temperature, for example. So those, and also you have the other category where it can be a manual valve where someone is literally out there physically opening and closing it.
Right.
Or it can be a control valve that you utilizing an electrical signal or an oil signal or a pneumatic signal. Again, we're not gonna go into that details in this section today. That's gonna be part of the process control kind of work that we're gonna do in the future. But for today, we're gonna highlight the role of valves in a chemical plant, how we are going to be sizing them, what different categories we have, And then we're gonna move forward from there to just simple approach, or just like brief approach of what are the pressure relief valves, what different types we have there, and how those type of pressure relief valves are being sized,
Right.
According to what.
Right.
So in slide 4, the valve classifications, like in terms of the physical, what they are doing, irrespective of how they are being controlled, whether by your arm or by a pneumatic or an oil system, they have two ways of categories. They have two categories. There's the linear motion and there is a rotary motion. The linear motion is pretty much like there is always like it's either moving in an X or moving in Y. You know, like there is always a specific linear motion as the name entailing.
That's cool.
The Cartesian kind of motion. So those are the most familiar type of valves
Yep.
that we're actually dealing with on a daily, like, you know, pretty common in the industry.
Yep.
They can be globe valve, they can be diaphragm, gate valve, an angle valve, or three-way valve. Those are the most, pretty much, the most abundant type of valves in a product. The rotary motion type of valve, those are like they kind of look like they have a very special dimensions and orientation to how the flow is going around. So it's gonna be like tending to be having some spiral or radial type of motion when the fluid is going through them. So pretty much you're not dealing with Cartesian coordinates anymore, you're dealing within that entity in some type of like either a spherical or a radial coordinate. So those are like, you're gonna find them like the ball valve or butterfly valves or some eccentric plug valve. The butterfly valve, most likely you're gonna see them on a cooling water system. Like in a cooling water system, you want to minimize the pressure drop and you're always needing that flow. You're not regulating anything in a cooling water system. So
That's
the
cool.
best thing about the butterfly is like pretty much a valve that can deal with a gigantic flow, doesn't deal with much erosion, and at the same time has the minimum pressure drop across. But when you need it to be shut, it will be shut.
That's really cool.
Just like that's why like those type of valves are normally used. You're gonna find them most likely in a utility or cooling water systems. Globe valve tend to be the most famous control type of valve.
Yep.
And the reason why, as you see from the picture there, they don't cause so much of erosion in the system. They tend to be having, relatively speaking, higher pressure drops. But at the end of the day, that's what their purpose is they need to be controlling. Gate valves, on the other hand, are mostly used in a process as a shut-off valve.
Yep.
Like an XV.
Yep.
They're gonna be like either on or off. So the perfect thing about them is they have minimum pressure drop. So whenever they are open 100%, you want that valve to be just like almost like non-existent in terms of pressure drop. You don't want to waste so much energy around them because they are literally 100% open or 100% like almost completely closed. So you want them to be doing their job without wasting so much energy. And that's basically the role of gate valve. Gate valve are not recommended to be used as a regulating valve because they are going to get eroded pretty bad.
Which means we're probably
They
going to
are
do
not
it.
designed. If you look at, yeah, the problem with the gate valve is like if you look at their design,
Yeah.
they are very restrictive.
Yep.
They are literally getting head-to-head collision
Yep.
with the fluid.
Yep.
So, given time, they are going to be eroding.
Yep.
They are not like having this sweet, smooth kind of like change of momentum around them like a globe valve would do.
I apologize. Did you hit on the ball valve?
Not yet.
Okay.
The ball valve is pretty much like it's doing the same work like a globe valve, but it has way more tight sealing. So ball valves are this type of valves that sits there between a gate valve and a glow valve in terms of like being an on and off kind of thing.
Right.
And at the same time can be used as control.
Yep.
And the reason why is if you look at the ball valve, it has this curvature to it that the gate valve is lagging. And because of that curvature that you have around the body of the ball valve, you tend to be like basically minimizing the erosion that otherwise you would have in a gate valve that has a very sharp edge. And at the same time, it has a very tight, it has more tight, tend to be having more tight sealing and potentially cheaper cost than a glow valve.
Right.
So now, like, after the classification, we move to the part of the valve sizing. So you don't be like get to be like saying, hey, I want a ball valve or I want the gate valve that has a linear or equal percentage. That's not how it works. What it works is that you have a process control. You have a given process variable that you, for example, you want to control. And that process variable, either you want it to be like reacting slowly or reacting aggressively fast. So, for example,
Hey, so
you're
real
dealing with
quick.
a natural gas.
Because I know before I met you, I'd never heard of a lot of this. So if you could just briefly explain, like, what is the CV? Like, what does that mean? And then as far as like the characteristic curves, like what do those actually mean in simple terms?
Yeah, so pretty much like if you have a, like, using the same terminology in electrical engineering, you have a flux, you have a current, you have voltage, and you have resistance. Or what we used to be calling in there, the reciprocal of resistance, conductance. So CV represent the current. This is pretty much, sorry, this is the conductance. This is the reciprocal of resistance. The higher the CV, the more conductive that valve to flow. So it means pretty much it will be allowing more flow for less dP, the higher the CV.
Oh, that's
goes.
really cool.
That's pretty much what it is.
Okay.
It's that's what the CV is.
Okay.
You might hear it as a CV or you might hear it as a KV. It depends on type of vendor. Like the English units would be using the CV. The SI units or metric sometimes use the K. But both of them are the same, physically the same thing. What they mean is that your dP is the equivalent of voltage. This is your pressure
Right.
difference. This is your driving force.
Right.
The Q, which is the flow through the valve, in terms of like here we have is a volumetric flow. That's pretty much your current. And the CV is the reciprocal of resistance, or just like the conductance. Now, that CV, it will be how, like, you know, the valve is not like stuck in 0 or 100%. It can take on 10% opening, can be 20%, all the way to 100%. So the start and the end of that valve, all of them are the same, because if it's sealed shut, nothing flowing. If it's 100% flowing at the same CV, 100% open, then you have a full flow for that CV. Now, what's happening between 0 and 100% is going to be dependent on what you're trying to do in the process. And what's going to be doing in the process is going to dictate what you are going to choose from what we have discussed in the previous slide. So, if I am dealing with an emergency, if I have a natural gas system, fuel system, and the fuel system reached a tripping high pressure, what type of reaction I need from the valve?
Right.
I need something that's super fast.
Right.
And that's pretty much what's going to happen. I'm going to be picking the quick opening type of valve, that's going to be the gate valve. So the gate valve has this quick opening shape. The red line that you have there, that's pretty much represents the a gate valve. Now, if you are in a process that you wanted to regulate, for example, pressure, and that pressure is, how can I say that, impacts the process significantly.
Right.
So you want that pressure to be as you know, moving slowly as possible.
You're wanting
as
tight
slow
control.
as possible, because you don't want to, you want tight control. So normally you're gonna be using the equal percentage.
That is very cool.
So that the process eventually ends up basically tells you that you're not like you don't have to get confused. Like people doesn't have whenever you actually like jumping into engineering firm or something, you don't need to get confused around that. Like I know you're gonna be like jumping there and someone like throw a manual in front of you, and basically the first thing comes to your mind, okay, well these shapes are nice and everything, but like first thing that's gonna come to your mind, okay, do I just pick anything or
Right.
like what? It depends on something.
Right.
And then you have the type of valve that's common that tend to be like basically if you have a CV at 90%, the opening of that valve at 90% would give you literally 90% of that CV. So if that CV is 100, for example, when you open 90% of the valve, that means the CV is 90, and that's what linear means. It basically mirror image of the opening.
Right.
Now, there are cases where you want the process, and again, it's going to be dependent on the process engineer or the process consultant, or which basically is reflected from how sensitive a given, for example, reactor is to change of your main variable. Sometimes they will come back and basically say, hey, I need this delicate balance, like where between 0 and 50%, I need it to be acting like an equal percentage. And then once it jumps beyond that, I need it to be acting quickly. Like for example, if you are dealing with an exothermic reaction and in the beginning, there is a range of temperatures that you want to be like moving slowly around, controlling the heat exchanger or controlling the temperature. But if the temperatures start to be jumping out of that zone into an exothermic system where a potential meltdown of the reactor can take place, then that's where you need that valve to be acting very quick. And that's where you have something called modified equal percentage or modified linear.
That is very cool.
Valve. That's pretty much is the customized thing. And at the end of the day, you're gonna go back to those same slide, like the slide we have explained earlier. And those vendors would be pretty much working around the bodies of those valves to basically produce the characteristic curves that you'll find fit and accurately able to control your process as you see fit. So, as we mentioned earlier, it's a driving force, flow, and conductance. But that brings up more two categories. If I'm dealing with a critical flow, the downstream pressure does not matter anymore, because like you are in a sonic case, you're in a sonic pressure.
Yeah, before you get too deep, can you explain the difference between critical flow and subcritical flow?
So critical flow, pretty much it means that the downstream pressure is way below something called the critical pressure. What the critical pressure means? Critical pressure means that's the pressure at which the gas has reached the sonic speed.
Very cool.
Any further reduction of the pressure downstream has zero impact on the flow.
Very
because
cool.
Pretty much like your gas phase can't see anything. It's in a state of shock. It can no longer relate to whatever downstream of it. So that's what sonic or critical flow means. Subcritical flow, which mostly you're gonna see that in liquid flow. Again, liquid flows can still have sonic flows, but for it to reach that point, the pressure drop has to be significantly high. Like it's something that's really, you wouldn't get accustomed to see that in industry.
Right.
So normally speaking, liquid flows tend to be always like 95% of the time to be subcritical.
Right.
On the other hand, any gas flow that you gotta deal with, most likely is gonna be the reverse of that. It's gonna be critical flow.
Well said. You ready to get to my favorite
Now we'll
topic?
move I know you're gonna. I was about to say that, and now I'm gonna be like moving to your favorite topic, which is like, it's Valve. I mean, like, I always like struggle. In the beginning, like you'd find like people struggling to do that concept, the pressure relief valves, or even a rupture disk. They are literally valves. They are just having more regulations around them because they are dealing with safety and they are dealing with hazard. Because at the end of the day, the pressure relief valve is going to need to protect an equipment, and it's going to need to protect the environment, and it's going to be like needing to be protecting the human beings around the plant. So the fact that pressure relief valves deal with health, safety, and environment, that's what makes it super unique and has a lot of regulations around. But at the end of the day, it's the same concept when it comes to sizing. But again, like we have mentioned earlier, you don't need to make it harder than it should be. If we are looking at pressure relief valves, there are codes and standards to go by. And I want to be stressing that fact. The codes and standards, like for example, ASME in the United States or PED in Europe, those are laws. So they are not like optional, like, hey, it will be nice to be following them. No, if you fail to follow them, this is a criminal offense. So you really need to make sure that you're at least meeting that.
Right.
Like, nobody's gonna be like telling you if you exceed, if you are becoming more, if you're having more regulation on your system that exceeds what the standard and codes are claiming, is fine. But the standards and codes are there to make sure that everybody is on the same page and everybody is talking the same language. It makes sure there is a consistency. Every time someone builds a plant, if someone is not aware of what this chemical plant is doing, but the fact that I know what type of fluid and what type of service I am dealing with, someone across the globe would be understanding what calculations you have done. And that way I can be able to regulate it.
And so the reason I was kind of joking with Mo, and it's a favorite topic of mine, I see more issues with this than I see with a lot of other things, as far as valving goes, right? Like, just throwing it out there. If you have the ability to isolate your relief valve, then you don't have a relief valve. If you don't actually know what your relief valve is doing, you don't have a relief valve. If you've never verified that your relief valve is actually in good shape, you don't have a relief valve. And there are some places where you need a relief valve and you don't have anything. And we kind of laugh and we joke about this, but like, I have actually seen relief valves go off. They have actually failed as designed. And so, from me being an engineer and me having operators under me, like, you do kind of worry what would happen if that relief valve didn't fail as designed. What if it wasn't there? You know what I'm saying? The reason we're talking about these things as laws, and it's, we kind of laugh about it, but they are actually laws because they are there to protect people. They're not there to design protect equipment.
Absolutely.
They're not there to design to protect companies. They're there to protect people and the environment and everything surrounding that.
I mean, that's definitely number one thing.
Right.
Like, basically to make sure nobody gets harmed.
Right.
And to protect the assets that you have. And of course, like, by protecting the asset, make sure you're protecting the environment.
Right.
Because otherwise, if that vessel bursts, everything in it is going to be just exposed.
100%. And so that's what happened to me, right? So I had a vessel that actually relieved. And it relieved as designed. It relieved below set pressure, and we did eventually figure out why that was. But one of the shortcomings for this specific example that I'm thinking of is, because we've talked about it, right? Sometimes when you relieve these pressure relief valves, right, you design a vessel to relieve into so that the contents aren't just everywhere. In this specific example, when it relieved, it actually just relieves directly into our parking lot and into the walkway in which we have people progressing. And hindsight's always 20/20, right? Like, that's obviously not a great design. because if it relieves while somebody's walking in the path, like, guess what? You know?
Absolutely. I mean, like, if just think about the layers. Like, the safety valves are literally like your process control failed.
Right.
The process control itself failed.
You've got it. Yes.
Your tripping system failed. Like, what, you know, beyond the process control, you have a tripping system that basically is supposed to engage whenever something dangerous occurs. You have this layer also fail. This is like literally the layer between. This is the last layer for you to be controlling anything.
100%.
Because beyond that, that's where like event will be reported.
100%.
Because like it either can be like something as local within the plant that's gonna be causing an issue, like you know, an injury or something.
Right.
Or it will be causing some type of fire that will be engaging the authorities, and that's where you 100%. Know it's really gone really bad. So that's where the safety relief valves are there for. Most of the times they are not doing anything, and that's 100%. What they are intended to be.
Yes.
Yeah. So I again have seen on different occasions that somehow a relief valve is being used as a control. They are not supposed to be doing that. Control valves are literally there because like every measurements that you have put in place has failed. And this is your last resort. You cannot be using a pressure relief valve to control.
That's really
process. Good. So just because they are physically are the same principles of how a control valves are operating, that's what they were not intended to be doing that. But again, to back up to our discussions, you are going to be finding so many codes and standards related to that. So it's going to be like the API 520, 21, 26, and 27. This is going to be like going through all the details of how a pressure relief valve is being sized. Now the ASME part is going to be like dealing in terms of like what type of pressurization scenarios, what type of like parameters that you're gonna need to put in your equation to be actually start to be like sizing those relief valves. So if you're dealing with like a heater, a fire, like a direct fire heater, like a furnace, that means if you have a relief valve there, you're gonna have to go to ASME 8. It's literally, you know, it's self-explaining. If you are dealing with a pressurized vessel, which again, I am not the one that basically specify what pressure vessel is. Like, I cannot be like saying, well, I can't, you know, I have a tank, but I don't see that as a pressure vessel. No, that's what the code is saying. And the code is going to even like define that for you.
Right.
It's gonna be like telling you above this pressure temperature. It's gonna be like telling you everything around that. If you are dealing with something that's exposed to a flame, you will need to go to ASME 8. If you are dealing with steam boilers, you're gonna go to ASME 4. If you are dealing with nuclear power plants, which is a whole different industry, ASME 3. If you are dealing with like a just simple, what's it called, like a steam drum,
right?
For example, you're gonna go to the unfired pressure vessels. This is pretty much like it's a pressure vessel, but it's not exposed to flame. And the reason why you have two segregation between fired and the fired is because the overpressurization scenarios are way more extreme when you're exposed to something that has a heat source versus that something that's just containing internal energy. So that's just like the reason why you have this type of standards.
And before we proceed,
and after you are sizing, and by the way, the most important part out of all these things, as a process engineer, after you're sizing those relief valves, it will be moving to the mechanical engineer, and then it's going to be moved through the whole procurement and everything. What's gonna need to be like verified later, not necessarily by a chemical engineer anyway. It's gonna be like pretty much like a material scientist or the quality specialist. with a certain certification, they will need to make sure, as you see on those slides, the stamp of the ASME on that valve. So not only you need to specify those relief valves, well, you're gonna need to make sure that those relief valve got the stamp of that code.
Yeah.
Because what you have sized on paper. But for someone to make sure that really physically doing what's supposed to do, it needs to get the code like the stamp verification, as you see there. How you can come up with a event scenario, and then you have many scenarios, you will need to pick the worst case scenario.
Yep.
That's basically your design is going to be. That's why we as engineers always end up being super depressed and pessimistic. Everything in our life has to be based on the worst case scenario.
Yes,
and unfortunately,
yep.
it becomes like a lifestyle.
Yes.
It basically,
you've got it.
Spreads out everywhere.
Yes.
Yeah. So now, like when it comes to the relief valve or the relief device procedure, how I can be sizing a relief valve? Again, the codes and standards are pretty clear over there. The guidelines are there. Guys, you don't need to be like really digging deep, especially around these things, because it's heavily regulated. All you need to do is just like know even like where you're supposed to be like picking your information from.
Right.
You don't even need to be memorizing.
Right.
You will pick it up. If you are an engineering firm, they have those guidelines. If you don't have the guidelines, that will be a problem. If you are an operation plant, normally if they don't have those codes, or those codes are somehow like old or something, like a hard copy, and it's not available to everyone, like you are in a different site or something, most likely all these codes are available online, and the company can purchase it for you, and it can be provided for everyone. But normally speaking, you're gonna need to define your loop. You have a given loop around the heat exchanger, for example, and you're gonna need to be picking the weakest link in that loop. Most likely, it's going to be a process equipment, not the piping. Piping is probably like the least of your concern, because like given how cheap, relatively speaking, the piping is, you're most likely protecting a piece of equipment, whether it's a heat exchanger or a distillation column or a reactor. That's why most of the time you're gonna find the relief valves are always like on a piece of equipment, not on a piping.
Right.
It's because the process equipment itself is expensive.
Yep.
And you always want to pick the cheapest thickness for that service, because there is a lot of fabrication and overhead costs that are associated with a heat exchanger than with just making a pipe to be rolled. So that's where that's coming from. That's not a generalized rule, but like most 95% of the time, it doesn't have to be 90%, but like most of the time, you're gonna always find the relief valve on a pump, on a reactor, on a distillation column. Always that piece of equipment is going to be like the part that needs to be protected.
You've got it.
It's not gonna be the piping itself.
You've got it.
Where the relief valve is going to be installed, it's most likely is going to be on the piping if that piece of equipment is too small. Because like just picture you're trying to put a relief valve on a pump. It's gonna be super hard in terms of like fabricating it. But like if you're talking about a reactor, for example, it's easier to do it because of how the size of the track. Or the size. The same applies for an absorber or distillation tower. Sometimes that's a pressure vessel. You don't want to be like making it extremely complicated by, inducing a weak point in the design by putting like some weird fabrication point or a weak welding point around there. So most likely you're gonna find the overhead piping, the header coming out of the distillation column that's going to the condenser, most likely is gonna have that relief valve, because it's gonna be servicing the same purpose but with lower cost. Now you're gonna need to locate the relief devices, and that's what we're talking about, what we just talked about. You're gonna need to define the overpressure scenarios. And that's like a whole long procedure that takes place in basic engineering and can actually find its way all the way to detailed engineering revisions. Because HAZOP or SIL classification might go through so many revisions.
Right.
You don't just do the HAZOP one time and it's just over. Some updates will be taking place, and whenever updates is going to take place, you're going to need to revisit all these documents to make sure that they are not introducing a new hazard that hasn't been already accounted for.
Right.
Now, choose the relief device types. Again, you are now in the area where you are not going to need to be thinking so much hard about it. It's going to be coming from a code. If you are in a Steam service, it's going to be like giving you boundaries for what your choices is. If you are dealing with a natural gas service, if you're dealing with like an oil service, if you're dealing in a nuclear plant, it's going to be like giving you some wiggle room or a specific device that will be installed there. If you don't have it, it's going to be like at this point, it's going to be like a matter of the expertise based on what older versions of plants has been taking place.
Right.
So you have codes. If the codes are followed and tend to be like having wiggle room and boundaries, yes, you can pick from that boundary, but most likely there is going to be like some established rule of thumb within that industry. Like, you know, if you're working in an ammonia plant or in a refinery or a nuclear power plant, most likely like you're gonna find rules of thumbs for picking which device is gonna work best fit in this case. And most of the time, the relieving system is not all about cost, it's all about reliability. How reliable that device will be acting when it has to act.
Right.
So keep in mind, we are dealing with a system that most of the time is closed, but when it opens, it needs to open. So reliability is a huge deal, and it's dealing with hazard. So you need something that deals with risk barely any time, and on top of this has to be reliable. So you can see it's not about the cost, it's all about like what has been established in that industry while meeting the standards of and codes that this industry must be following.
You've got it.
Again, like we mentioned earlier, a relief valve, at the end of the day, it's a valve.
Yep.
It obeys the same physical laws that we have talked about in a just simple valve. It doesn't matter if it's opening to atmosphere or open to a vessel that's at 1 bar, for example, or 14.7 psia.
Right.
So, like we have mentioned earlier, again, the only difference is that this time you're gonna need to consult like the API code called API RP 520 of what critical and what subcritical means.
Right.
So before we knew like it's a like more general term, has more flexibility around it. There are codes assigned for it, but like in our case, they have to completely regulate what that means. Because again, it's an HSE issue.
Yep.
So everything has to be completely quantified for someone that's sitting in Louisiana versus someone sitting like in Washington or someone is sitting in Texas. At the end of the day, all of them understand what that means. When someone says critical flow or subcritical flow,
right.
There's no wiggle room around.
Right.
And it's the same formula each one of them are using. If you have a critical flow, which basically is a function of something called the specific ratio, it's known as K or gamma. It depends on like what thermodynamic class that you have attended. Sometimes you associate it as K, sometimes you call it gamma, but at the end of the day, it's the specific heat at constant pressure divided by specific heat at constant volume. But again, that's pretty much what it is. If you're down, if whatever vessel or the downstream pressure that's being relieved to happens to be below that critical pressure, that's a critical flow. And that means you're gonna have to go to that formula on the right side. That's what it means. If the critical pressure tend to be like lower than the downstream pressure that you are relieving into, most likely in gases that's not going to be the case, most likely that's going to be the liquid case, then you go to the left side of that formulation. It's that simple.
Very cool.
So yeah, I mean, like the example that we have, for example, is a propane tank that you already had the heads-up meeting. You already went through the whole worst case scenarios, and you have established that your design basis is going to be a fired case, which you can see from the top left. The pressure vessel is a propane tank.
Right.
The design basis is a fire exposure. The relief load based on the fire case is 84,000 pounds per hour. The fluid that we have is propane. Operating pressure is almost atmospheric. The back pressure, now the back pressure is essential because if you have to completely define that, because if you are sharing a header with other equipment, like a header that's going to a flare,
Right.
most likely your back pressure is not atmospheric
That's very well said. Yeah.
because that system might be having some pressure in it. And you have to account for that because your driving force is going to be impacted. However, if you are dealing with a critical pressure anyway, that won't matter anymore. Whenever you are dealing with a critical pressure, it doesn't matter because the pressure downstream is no longer impacting anything. It's at this point, the orifice size is going to be dictating that. But just to go through this example, you have your back pressure is specified as constant. There are cases where the back pressure might be variable, but not in this example. I just wanted to give an overview, like in general, like what's going to need to get into your calculation, into the chemical engineer as a process input before you start sizing. How he get to that, it's a whole different animal in its own.
Right.
But for now, this is the example. So you go from there and you are going to understand, hey, I have this fire exposure. So as you can see from API RP 520, which the table below it is going to tell you if you are fire exposure, you will need to do the overpressurized case is going to be 120% of your set pressure. So if the set pressure is 100, then it's going to need to be 121 psi. Why? That's what we're going to be discussing. So your design basis is going to tell you if it's a fire case or not. If it's a fire case, pretty much it doesn't matter what you're sizing, how many relief valves that you have. You're going to have to size your overpressurization scenario is going to be 120 because that's how extreme it is when you have a fire.
Very
The
cool.
fluid is specified, the pressure is specified, the relief load is specified. You go to the middle section of the example here of the slide, and you get your thermodynamics revisited again, where you will be picking your compressibility factor, your actual DP versus the critical DP, and you can actually get the pressure. There is actually like beyond the simplistic view of like relating the critical pressure and the upstream pressure with the specific ratio. There is actually another relationship between the sonic speed and the critical pressure. And the sonic speed is way more strong because it's actually like it doesn't matter if it's ideal or real gas, it will be generalized formula. It's gonna be like telling you, here is your sonic speed and here is your critical pressure. From the critical pressure, you're gonna get the critical DP. And you already know the actual DP. If your actual DP to critical DP is below 1, well, you are subcritical. That's when the back pressure matters pretty much. Because if you're subcritical, the downstream pressure plays a very big important role in your calculation.
Very cool.
If you end up like bigger than 1, it's going to be a critical flow, and pretty much the relief load, it will be dependent on the orifice diameter because the sonic flow is constant at this point. So what's going to matter how much mass? It's going to be density multiplied by area multiplied by velocity. So, V is constant. You cannot increase the sonic velocity. And pretty much like the only thing left is the area, which is the orifice area itself. Compressibility factor, of course, most likely you're gonna deal with non-ideal behavior. Nothing is ideal. That's why you call it ideal.
Not everything was ideal.
Because it's never ideal. That's why you call it ideal. So that's pretty much, this is the output of the thermodynamics. Whether you're doing it
right
by tables, equation of state, or you're doing it by simulation. Equation of state, activity model, viral equation, whatever you want to name it, that's where it's coming from, thermodynamics itself. Now you move to the standards, which is the last section of that slide, the far right side. That's where you have like API 520 and API 2000s. And what's going to be like telling you, if you have a conventional pressure relief valve, and you already know the back pressure, you already know the overpressure. See, the overpressure that we were talking about earlier, because of the fire scenario, it's 121% of the set pressure. That's where it's coming into here, into these calculations.
Right.
And you add that to the set pressure, which is basically, that what you not need to exceed in the heat exchanger, for example. And you're already aware of the back pressure. From there, you're gonna get something called the F2, which is basically the actual relief pressure, like the effective back pressure. That's what it means. So, if your back pressure, how I can say this? If you have a back pressure that you did not account for, versus the rated capacity back pressure, like you assumed it's atmosphere,
right,
and now the capacity with the back pressure end up being like less than 1, the ratio there ended up being less than 1, you're gonna have to account for that inefficiency. That's why that factor is embedded in that standard and code kind of relief method calculation. And that's why, like, if you are in sonic flow, you're always gonna find this to be 1. If 2, most likely is gonna end up being 1 in gas service. Why? Because it doesn't matter. That's what it means. The back pressure doesn't matter, because it doesn't matter. It literally becomes independent of the back pressure, and that's why it ends up being 1. And once you are coming up with this, you're gonna see the calculations in the bottom. You have your temperature, you have the mass flow rate. Now, there is that KD. What is the KD? It's a coefficient of relief. And that either can be provided by the ASME or the manufacturer. So the relief valve manufacturer or the ASME code is going to be like telling you for a given service, for a given pressure range,
right,
this is what the KD is. Most likely it's going to be around 0.65. The compressibility factor, you already got this from thermodynamics. The set pressure, you already has been specified in your relief, because the tank was designed to handle this type of thing. The back pressure, you already have it, and you already came up with all these things in the chart. It becomes straightforward. From the formula that we had in the previous slide, you will know the required area in a square inch. And just make sure, please, make sure that the mass flow rate has been transformed into pounds per second. And you make sure that you have changed the feet square back to inch square. It always happens. People always have this units confusion. Just make sure that your units and your formulas are consistent.
Right.
Because most likely the load is going to be per hour, and your area gonna come out of this formula either meter square or square feet. So make sure that you're always taking care of those units. And keep in mind not to mention temperatures and pressures, all these things. Make sure that they are consistent, because there is going to be in that formula universal gas constant. It's a constant, but it's a constant based on whatever function, units you're using. So don't forget all of these. Anyway, after you are doing this calculation, you're going to find out that the required area is not going to be exactly around the standard area. It's going to be somewhere between two standards, one smaller than the required and one standard higher. I mean, without telling, you're going to have to pick the higher one.
Right.
But like normally, if you want to be sizing an orifice based on your calculation, you can, but I would seriously doubt any manufacturer out there that's gonna be like designing an orifice to a second or third digit. So decimal, sorry. So make sure, like, after you're done with the required area, you're gonna go to that chart that you see there, and it's pretty well established. Every letter has a given standard inch square area. So in our case, we have around 0.4. That means you are going to need to be picking orifice G, which is 0.503 from the chart that you see there. So that's just like a simplistic approach for our example. Another example of like how a relief valve is being sized. This is the steps that you will be going through. You're going to be like having multi-input. There's going to be like output of a HAZOP. There's going to be like a code that you're going to have to be following. And you are going to be incorporating transport properties and thermodynamic properties of what we have learned at school. So I hope like this has been helpful. And Brandon mentioned several times, you can always reach out to us on by email or on YouTube. Even you can comment on our YouTube channel of whatever feedback you are interested in. We are always going to be valuing all your feedback, irrespective of how it looks like. Every single feedback is always appreciated and welcome. And that's everything on my end.
Yeah, so if you want to go to that last slide, I just want to say thank you again for watching. Really do hope you enjoyed. Hopefully you got something valuable out of this. If you too want to have Mohammed size your relief valve, all you got to do is send an email to sciencemadesimple@outlook.com and write me a check for $250, and I'll have him do that for you. But for real, I really do hope you guys got something out of this. I know that I did. Like I said, this is something that you will, if you look long enough, you're going to start to see this in industry and see these gaps. And so the more of us that are aware of the regulations and kind of how you handle that, the better we'll all be. Find us on YouTube at Scientifically Simple. Like Mohammed said, leave a comment, leave a review, let us know what you think. Feel free to reach out. And that's all I got. Signing off.
Thank you.